Okay, I'm going to talk to you for a couple of minutes about phase relationship. So you already know from class, I think, that, and from here, that distance versus time for an oscillating mass like this would look like a sine wave, right? Also, velocity versus time would look like a sine wave, and so would acceleration versus time. Now, if you were going to put those on the same time axis and try to look at them in time coincidence, so distance, velocity, acceleration would all three be sine waves, but their phases would be different. In other words, their peaks and valleys and zero levels wouldn't be the same. Okay, so how exactly would they line up? Well, you might have learned something in class about taking derivatives and doing it that way. There's also kind of a more practical hands-on way, and that's what I'm going to show you here. So I'm going to explain some of this that you'll need to know to do step 4. I'm almost going to give some of it away practically, so you'll probably want to listen up pretty close. So let's say about velocity. Let's say we've got this thing moving, okay? All right, so we've got simple harmonic motion going on. Now, just kind of think for a minute. This thing is moving all the time. Is there ever a time when the velocity is zero? Okay. Your first instinct might be to say, well, no, it's moving all the time, but think a little bit more carefully. There is going to be a time during any one cycle where the velocity is zero. Okay. And I'm going to leave you to ponder that a little bit. Remember back earlier in the semester when you had projectile motion in class, and say if you threw a ball up in the air or shot a cannonball up in the air or something like that, then it follows a parabolic path. But there was a point at which the vertical velocity, at least, would have to be zero in order for the cannonball to change direction and start falling after it rolls. Okay, so that's kind of the same thing here. Maybe that'll give you a hint. Okay, now what about maximum velocity? The velocity doesn't stay the same all the time. Well, once you've figured out where the minimum, or well, the zero velocities would be, there's actually more than one, you can pretty much assume that, well, it's going to be slow. It's going to be moving slowly when it's close to those zero velocities because it's slowing down and getting ready to hit zero, or it's speeding up after it's just been at zero. So somewhere farther away from that, like maybe somewhere in the middle, might be where the maximum velocity would occur. Okay, so think about that for a little bit. Hopefully that'll give you a clue. All right. Now, what about acceleration? Okay. Acceleration's a little tricky. It's a little hard. Usually when we do this live in class, face to face, I usually tell people, well, we'll cheat a little bit when it comes to acceleration, okay? And here's how we'll do it, okay? Okay, so let's assume I've got that perfectly steady. It may still be wiggling a little bit. So now we're not moving right now. We're sitting still. We're just hanging there. But what would the total force on the mass be at this time? Okay, let's assume it's perfectly still. It's not really moving. Well, it's not moving, and it's not moving for a sustained time. So what the total force on it would have to be zero, right? If you guess zero, then you got it right. Okay, so the spring is pulling up on it, and the mass's own weight is pulling down. Now, when we set it in motion, okay, now it's in motion, but in the middle of this path, it is going to pass through zero. So it's moving, but at that instant in time when it passes through the zero, the forces on it are the same as if it was just hanging there motionless. So actually the force is zero when it passes through the equilibrium point, okay? And consequently, you could also say the acceleration is zero. How do we know that? Well, because force equals mass times acceleration. So if force is zero, there's no way acceleration couldn't be zero, okay? The mass is certainly non-zero. Okay, so force is a little bit easier thing to kind of get a gut feeling for than acceleration. Now, what about while it's moving? What happens, say, let's say I stop. Okay, so like I was just saying, total force on it would be 0, on the mass would be 0 when it's hanging at equilibrium, all right? What about, is there a way that we can figure out how force is behaving at other positions? Okay, what if I took my fingers and just pushed it down? So if you were here in lab in person, you could do this. And you can imagine, you can probably already pretty well tell that if you pushed this mass down a little ways, you would feel it pushing up against your fingers, okay? So you can imagine that, right? So that tells you that anytime the mass is located below the equilibrium point, then it's experiencing an upward force then, or a positive force. Now we're using a static measurement to determine that, but the configuration of forces, not counting your hand, but the force that would come from its own weight in the spring, the other forces would be the same when it's actually moving in simple harmonic motion. So you push it down, you notice that the mass is pushing up against your fingers, and if you could push it down farther, you can probably imagine that it would get harder. You would feel the mass pushing up against your fingers even harder, okay, with even greater force, because you're stretching that spring even more. So that tells you that the force, the upward force, gets bigger the lower you go, okay, with the mass, all right? So what have we figured out from that? Well, we figured out anytime the mass is below its equilibrium position, it's experiencing an upward force, and that force would be getting greater the farther down you go below equilibrium position, okay? What about the other direction? This is a little bit harder to grasp intuitively, I think, but we'll do the best we can. But if you were here, you would be able to notice that, okay, you could lift the mass and you would feel it trying to push down against your fingers, right? So that tells you that when the mass is above its equilibrium position, that it's experiencing a downward force or a negative force, okay? And this is the part that's maybe a little harder to imagine, but you could push it up a little ways and you would feel the mass pushing against your fingers, and you'll feel it pushing downward even harder the higher you lift the mass, okay? So that tells you that the higher up you go, then the greater a downward force that the mass is experiencing, okay? So we figured out two things there. We figured out that anytime we're above equilibrium, the force is downward, and the higher up we're above equilibrium, the higher position that we go, the greater height we go, then that force is even greater in magnitude, okay? Greater in absolute magnitude. So now that's assuming you don't lift it far enough to take it off the spring, of course. So that would give you some idea. Hopefully that'll give you a clue as to where the greatest downward force is, which would also be the greatest downward acceleration, which is the same as the greatest negative acceleration. So that'll help you some on question 4. All right.